So in this video, I would like to talk about derivative, which is one of the most important mathematical technique that is heavily used in physics. So derivative equals to getting a slope of a graph. And the formal definition of derivative is d dx of the function f of x, or it can be also known as f prime of x, equals to limit as h goes to 0 of f of x plus h minus f of x divided by h. What this definition means is that the definition of slope, the definition that we learned in algebra, is change in y divided by change in x. So for some graph f of x that looks like this, if I want to take a slope, if I want to calculate the slope at x naught, then what I do is that I take an infinitesimal increment. This distance would be h and would be very small, much smaller than 1. And at this point, change in x is simply h, and change in y would be f of x plus h minus f of x. So therefore, the slope would become f of x plus h minus f of x divided by h. Now, this limit term, what this means is that this h, like the distance in x, is going to be much closer. It's going to get closer and closer and approaches x naught. So therefore, like, the actual value of the slope would become more accurate. There are some rules for differentiation. And the first one is, if I take a derivative of some constant times f of x, then this simply equals constant times the derivative of f of x. And the second one is, if I take a derivative of sum of two functions, then this is derivative of the each of those two functions. You can kind of think of this as a distributive property of this derivative operator. It's distributed on f of x and g of x respectively to result in f prime plus g prime. And the third rule is that derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. So let's go over some examples of derivative. So first example is f of x equals to x. This is pretty simple because f of x equal to x is just a linear graph. And if a graph is linear, then remember in algebra we said the slope equals to the coefficient of the linear term, in this case equals to 1. If f of x equals to x squared, then we plug it into the definition of derivative, which is limit as h goes to 0 of x plus h squared minus x squared over h. And if we expand this term, this is x squared plus 2xh plus h squared minus x squared over h. X squared can be cancelled, and I can cancel off the h term, in which this becomes limit as h goes to 0, 2x plus h. Sorry about that. So from here, since h is approaching 0, we can safely neglect this term and therefore conclude that f prime of x equals to 2x. Now, for any polynomial, let's say f of x equals to x to the nth power, you use similar technique of expanding x plus h to the nth power, and if you plug it into the definition of derivative, what happens is that this exponent drops as a coefficient. So f prime of x equals n times, and the exponent, you have to subtract it by 1. So the derivative becomes n times x to the n minus 1. So for example, if I'm taking a derivative of 3x cubed, then from the first rule that I talked about before, this equals to 3 times derivative of x cubed, which is 3 times x squared, equating to 9 squared. So the next example is f of x equals to e to the x. In this case, f prime of x is also equal to e to the x. Now this is an interesting function because the derivative of that function equals to that function, which is not that common. And the next is trigonometric functions. So f of x equal to sine x, then f prime equals to cosine of x. If f of x equals to cosine of x, then f prime equals to negative sine of x. Now, you have to be careful on this negative sign for cosine because many people, since cosines and sines are related in terms of derivative, they sometimes forget about this negative sign. But for me, how I remember is that whenever there's like a c for trigonometric function, there's always like a negative that is attached. This is also the case for cotangent of x and cosecant of x. But we're not going to talk about the derivative of these functions as they're not commonly used in physics. So an important rule in taking derivative is called chain rule. And definition of chain rule is that derivative of function f of y of x equals to derivative with respect to y of f of y times y prime. So for example, f of x can be 2x plus 3 squared. In this case, y would equal to 2x plus 3 and f of y would become y squared. So therefore, if I want to take a derivative of 2x plus 3 squared, then this is simply derivative with respect to y squared times y prime, in which derivative of y with y squared, this is just same as derivative of x squared, since it's just the variables that's different. So therefore, this equal to 2y times y prime, and 2y equals to 2 times 2x plus 3, and y prime is just the slope of this linear graph, which is 2. And if I expand these terms out, this becomes 8x plus 12. Now let's actually verify this result. So 2x plus 3 squared, if I expand this becomes 4x squared plus 12x plus 6. And therefore, if I take a derivative of 4x squared plus 12x plus 6, then this term becomes 8x because this 2 is dropped off and the exponent you subtracted by 1. This term is just 12 because this is linear and I just take the coefficient. And since this is a constant has zero slope because it does not vary with x. So therefore, we verify that the chain rule led to the correct derivative value. Now, using chain rule, one application is taking a derivative of the form f of x divided by g of x. This is also known as quotient rule, in which in school teachers are going to tell you to memorize it. But the proof of this is that derivative of f divided by g is in the form of derivative of f of x times 1 over g of x. And remember, from product rule, this becomes f prime of x times 1 over g plus f of x times 1 over g of x prime. And derivative of 1 over g of x is simply, I take the derivative with respect to g of 1 over g and times it by g prime. Now, since this equals g to the power of minus 1, the derivative with respect to g would become negative g to negative second power times g prime, in which this would be negative g prime over g squared. Now, if I plug this value back into the quotient rule expression, that would become f prime over g plus f times negative g prime over g squared, in which if I multiply multiply g on both the denominator and the numerator here, then this becomes g squared over f prime g minus f times g prime, in which this is the form that you learn in school of what quote-unquote quotient rule is. Another application of chain rule is implicit differentiation. Now, this is taking a derivative that is not in the form of y of x equals to blah, 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 blah. So for example, equation of a circle let's say of radius 1. The equation is x squared plus y squared equals to 1. This is not in form of y equals to f of x. Instead, it is an expression of both x and y. So what you do here is that you just take a derivative of this whole expression, in which this becomes 2x. That becomes 2y times y prime from chain rule, and the right hand side becomes 0 since 1 is a constant. So if I solve for y prime in this expression, canceling out to 2, y prime equals to negative x over y, in which it is a function of both x and y. It is not like a clean version of y prime equals to some function of x, but still it is a useful technique to get a derivative of implicit functions. Now in the last application is getting derivative of inverse functions. So for example, natural log of x is an inverse function to e to the x. So therefore, from the definition of inverse function, e to the ln x equals to x. Now from here, I take the implicit differentiation, in which the left-hand side becomes e to the ln x times ln x prime, because I first take a derivative with respect to natural log of x, in which it is going to be e to the natural log of x, times the derivative here. This is again aligns with the chain rule that I talked about before. And the right-hand side becomes 1, since derivative of x is just 1. Now notice how this expression that is simply just x times the derivative of natural log of x equals to 1. Therefore, the derivative of natural log of x is simply 1 over x. And using chain rule, I can get inverse functions of basically any functions that I want to get.